So let's finish off 5.3 and talk about least squares solution. So where we're at is that 5.3, if you're told to solve AX equals B, but B is not in the range of A, then we have no solution. We would just simply say inconsistent. But we're going to restrict this problem to say, okay, fine, it's inconsistent. But let's take a class of this problem, and what we're going to do is say that if A, m by n, but m is greater than n, this is an over-determined system. So I have an overdetermined system, and not only do I have an overdetermined system, when we calculate the rank of A, what's the rank? What does the rank count? That means when I take A, I put it into row echelon form, and I look for lead variables versus free variables. What does the rank count? The lead, right? So M on a system, M represents what? The rows, which is what? Equations. What's N represent? The variables. And if the rank of A is N, what is that saying?
That you have extra equations in there.
Well, we know there's more equations than variables. That's what that says. The rank of A being N says there's no free variables. And so we're going to consider the problem so that this is an overdetermined system, but more importantly, we have no free variables. If I had free variables, we all of a sudden get to what possible things? Either strictly, if we would just do a system like this, overdetermined systems are either no solution or an infinite number of solutions if we have free variables. If I say there's no free variables, we've actually reduced it to what? No solution or one solution, right? Now, what we're doing is you either have none or exactly one, and you don't have exactly one. So what do I do? And so that's the type of problem that we're looking at. So we're looking at this particular thing. Given that this is what we have, so we're going to just simply study these. What we're looking at again is A is this actor of a certain sort. A is spitting out from Rn to Rm. So over here is Rn, over here is Rm. I'm going to write this a little differently in terms of pictorial. I'm going to write this nice little plain looking object here to be representing the range of A. And over here is x's. And we know that, so my problem looks like this, where m is greater than n. So A is taking nth dimensional space and spitting out a space of higher dimension. What's going on is this entire space, all of Rn under A, is getting mapped only to the range of A, which is this over here. So I'm going from a lower dimension into a higher dimension. This higher dimensional space, the range is this particular object. And then what I'm getting as well is if you're asked to, so here's my B. And so if you're told to solve AX equals B, but B is not in the range of A, we would normally just simply say no solution. What we're going to do is we rethink the problem and simply say, okay, instead of just saying no solution. Let's make a new problem. And the new problem is this. Can I find x hat such that a of x hat is close to b? And how do I do that? So there, over here, a of x hat is obviously inside the range of a, because a times anything is the range of a. And so that's a of x hat. And over here is some sort of x hat specifically, so that it's close. Obviously, it's not b, and I can never get to b. I want this to be close. And so the problem becomes the following. And we call this the least squares problem. And really, this is kind of, I suppose this gets to a technique when people interview you, and you really don't want to, you have your own list of things you want to say, and they can actually ask you any questions that they want. If you want to cheat, you could do things like this. If they ask you a question that you don't want to answer, you could say, well, I'm going to reinterpret that question as my question, and then answer your own question. So it's kind of cheating, right? Somebody asks you something kind of personal. It's like, well, you know, did I actually show up today? Yes, I did show up today. And they're like, well, that's not what I asked. But I answered a question, right? So the people say, hey, solve ax equals b. You asked me to solve ax equals b. I can't solve ax equals b. You know what? I'm rather going to solve this problem. But that's not what I asked you to do. So I can't do that, so I'll do this. Okay, so it's a common technique in discussions. I probably just gave you bad ideas. No, anyways. So you're given ax equals b, and we want to minimize, and what we do is we're going to let r equal b minus a x. This is obviously, this r is actually a function of x. What we're doing is, here is your range, and then here is my b, here is my ax, and then there is my r. This particular r is called the residual. So the residual is, you know, kind of like your leftovers, right? You would say, hey, what's left over? This is my wrongness. And so what do I do is, what I need to do is find every single residual for the infinite number of possibilities for ax and pick the smallest. Picking the smallest such thing is the same thing as, you know, picking its magnitude, but the magnitude involves the square root. So instead of minimizing r, I'm going to minimize this r of x squared, which is simply actually the magnitude of just simply b minus ax squared, for all x in Rn. So that's my least squares problem.
The magnitude of r of x is the x plus b.
X plus b. Which? This magnitude of r? So r is b minus ax, right? Which is b minus everything that a can be mapped to, which ends up being this entire plane. So ax as a variable is the entire range. And then what we're doing is we're taking the magnitude of r squared, which is the magnitude of b. Since those are the same thing, it's just the magnitude of b minus ax. What we're really, if you look at this part right here, this is saying find every difference between b and the entire range, right? Take everything in the range and take b minus it. And when is that as small as possible? So this is a minimization problem. And if this is true, the solution, x hat, is called the least squares solution. Is everybody okay with? It's the least of the square. It's a minimization of the square object. All right. Two issues. Solve this problem. All right. Two things I would like to know. One, does it exist? It's kind of silly to start looking for something that does not exist. That isn't an actual common thing that we have to do. I mean, there's one of the things I've shared in like practically every class when I talk about this existence question was one of our professors had, when he was getting his degree, had a friend getting a degree, and they were working on a branch of mathematics doing these toys and rules, did all these wonderful things, proved all these particular theorems, and then finally sat down and asked, is there anything in the set? You have toys and rules. You've done your toys and rules and everything you did. What are the toys? And so he sat down and worked it all out, and the answer was nothing. It was empty. So what he did was he found all these properties of the empty set, which was pretty well studied and well known. And it was like, all right, great job working for a couple of years on this without looking for the existence question. So you have to hit it first, right? Does a solution even exist? And if we don't have the existence, there would be no point in looking. And so that's the first thing that you have to do. Then if it's like, okay, if it does exist, can you find it and is it unique? And a lot of times the process of showing that you can find it also shows that it's unique or not unique. And so the first thing that we have to ask is, exist. Does this x hat actually even exist at all? Can I actually look for some sort of minima? And so in other words, does the minimum exist? All right, we have a theorem. And what's nice about this theorem is the theorem doesn't actually even talk about the range of A. If we are given S a subspace of, say, Rm. Now, we're interested in a particular subspace, but this particular theorem on the existence actually works for all subspaces. It doesn't matter. And so for any particular subspace that you want, for any B that's in Rm itself, there is a unique P that is in that subspace that is closest to B, and how do you know that? If you would take B minus this thing in your subspace, it's always smaller than B minus Y for any Y that is not in P Y in the subspace. If and only if B minus P is in the orthogonal complement. The proof is in the text, and you want to kind of go through it. The idea behind it, really, when we look at these particular shapes, visually, if you want to kind of visually understand it, if we have this point in this particular vector here, that really what it's saying is the shadow underneath it, right? This projection exists, and this difference is as small as possible only when it goes straight down with no contribution. And straight down with no contribution says that it has to be in the orthogonal complement. So really it's just a statement of the projection. We take this, we project it upon an arbitrary vector within the subspace. The only way that this happened was you went down a vector that is completely orthogonal to every vector within this subspace, which would be, it has to be in the orthogonal complement. So that's what's physically going on within this proof. So that just simply says, hey, it exists. And how do you find it? Go straight down orthogonal to the subspace itself. That length is the smallest length that you could possibly get. And then that means this guy obviously exists. That's what we were looking for. Hey, since this guy exists, and it is in the orthogonal complement, he obviously exists. It has a shadow. All right. Now that existence is okay, our problem now looks like this. So for our problem, the subspace S, what we're really talking about is the range of A. And so by the theorem, there is a P in the range of A that is actually closest to B. In other words, what we can have is that B minus P squared is a min. So we have an actual solution. And not only that, this B minus P is in what? The range of A's orthogonal complement. What's the range of A's orthogonal complement? The null space of A transpose. Remember that picture that I drew like on the last class and the class before and the class before? What's the right-hand side look like? The null space of A transpose is always orthogonal complement to the range of A. So by the way, it is closest. Not only is it closest, it means that the difference of the two must be in the orthogonal complement of the range, which means it has to be in the null space of A transpose. And so there does exist an X hat so that AX hat is equal to P. So that's our nice little existence here. But this is useful. So some sort of X hat exists so that A times X hat actually does get us to the close. How close do you want to get? You're going to get to P. That's the closest. How do I get there? I find my X so that when I multiply it, it gets there. So these two here can go together and say, hey, you see that P? Get rid of it and just write AX hat. And so what that tells us is, putting those two together, says that, hey, B minus AX hat is in the null space of A transpose for this solution X hat. All right, what does it mean to be in the null space of A transpose? What's it, if you're in the null space of a matrix, what does that mean? That matrix times it spits out 0. So if you're in the null space of this matrix, if I took that matrix and multiplied it, what would always come out? 0. So being in null space of A transpose says A transpose times it is 0, which is actually 0 of Rn. It's the left-hand side. But that's just matrix, and so that can multiply through, right? If I multiply this through, that means that A transpose B minus A transpose AX is still what? 0. Can I add this to both sides? If I add it to both sides, that says what?
A transpose B.
Let's put the X on the left-hand side. Must be equal to A transpose B. So that means where x hat is our solution for the least squares. So the problem has become this. What is the least squares problem? The least squares problem started out as, if we write way back here, what's the least squares problem? Minimize this right there over the entire range of A of the infinite number of x's. Please find the minimum. By using a couple of theorems, what this has been reduced to is if you have a solution, it solves that, which really means that, oh, I need to, so the least squares problem is now solve A transpose A x equals A transpose B. So my entire minimization problem has gotten rid of the word minimum. It says, I know I have it. Where is it? It's unique. And this unique thing has these properties. What property does it have? It has that it's actually the solution of A transpose A times it equals A transpose times B. All right, this is obviously, if I look at this, that is just a matrix, right? It's just a matrix. I could call it M if I wanted to. What is this? It's really just a vector, because it's a matrix times a vector, which is a vector. So when I say solve, it might look weird, A transpose A times x. Really what this is solving this M x equals C. If we go all the way back several chapters, we've solved matrices times x's equals vectors over and over and over. When could I solve this? When does this have a solution? And an M is invertible. What are all the words for M being invertible? What are the things that we've done? We've used, is it non-singular? Another theorem besides being non-singular is that the homogeneous system has exactly how many solutions? One, which is the trivial all zero solution, right? The only way to solve this is if that is invertible, which means it's non-singular, which means that mx equals 0 better only have the zero solution. Is everybody okay with this? So using all of that stuff simply says that looking at that, to solve this really means is that A transpose A better be invertible, which means non-singular, which means that A transpose AX equals 0 has only trivial solution. Remember how I've done that theorem? We remember at the very first test I said we need to know these three things, how they all weave together, because it keeps showing up. And this is the guy that we're going to use to the fact that this thing does actually have a solution. But this thing will only have a solution as long as there are no free variables. That's where the requirement, everything up to now didn't require free variables. The only way that this thing can have a non-trivial solution is if I have no free variables. And so we get the next part. How do I solve it? Finding the solution. And so what we have is the following theorem. A, m by n, m greater than n, rank of A equal to n. So what do I have? an overdetermined system with no free variables. That's what we're talking about. Then A transpose A X equals A transpose B has a unique solution, and that solution is the least squares problem solution. So I just simply set it. It really says, like, hey, look, it has a solution, which would mean what? You would take the inverse of the other side. And so if it has a solution, that would mean that the x hat is simply what? A transpose A inverse all times A transpose B. But that would also tell you that the projection P is AX hat, but what's that? That's A times that stuff, which is A transpose A's inverse times A transpose B. If I wrote all of that stuff out, that's a matrix, that's a matrix, that's a matrix. I could take all of those matrices and jam them together and make one matrix. And what would that one matrix do? It turns B into P, which is the projection matrix. It's the thing that spits out the shadow. And so if you want to, you could actually call this whole A transpose A inverse times A transpose equal to P is the big matrix. Is the projection matrix that turns B's into P's. Spits out the thing closest onto the range of A. It's just if you want to find it, but it's that whole mess. In the end, though, we have to solve this system. Good question is why. You know, the idea of the proof here. The why just simply gets down to this. A transpose AX equaling A transpose B has a solution if A transpose AX equaling the zero object has only trivial solution. Because what I'm saying is that you can invert it and move it to the other side as long as I turn this into the homogeneous system and actually say it has only the trivial solution. So what I want to show is that the only thing that makes this thing zero is if x is what? Zero, right? So what I want to start off with is, hey, if this is true, so this is where we start. So we assume, let's go ahead and assume that A transpose A x does equal to 0. And now we want to do some work, and I want to show, blah, 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 a lot of work here, that x has to be 0. That's the only thing that's going to work. All right, first off, if you see this, so we start off here. A transpose times AX equals 0. What does that tell you about AX? It says, well, A transpose times this is 0. So that means A transpose times something equals 0 tells you that the something that you multiplied has to be where? This says AX is in the null space of A transpose, right? A transpose made it 0. This thing has to be in its null space because it nulled it. Everybody okay with that? But obviously, AX is actually in the range of A. Why? What is the range of A? A times anything is in the range of A. Is everybody okay with that? So where is AX? It's in the null space of A transpose, and it's in the range of A. Anybody remember that little thing that I had over here in Rm, and we had this little thing right here? There's the null space of A. This is the range of A. Sorry, that's the null space of A transpose. What is the only thing in common between both of them?
There's zero space.
The zero object.
Yeah.
Hey, it's in this space. Okay, it's in that space. And it's in this space. Oh, it's nothing. So that immediately says, so that implies that this AX simply is 0. Now, because the rank of A is n, says what? No free variables. That's a homogeneous, which is a homogeneous system. Homogeneous systems have what possible answers? 1, the trivial, or infinite. What's the only way to have an infinite number of solutions? You have free variables. So homogeneous system says the trivial solution or an infinite number of solutions. Hey, by the way, the rank's n. There's no free variables. So that means a homogeneous system with no free variables together says only trivial solution, which implies that what? It has to be 0, which tells us the original has only the trivial solution, which has to be invertible. So we're done. What I like about that discussion is it goes through all of these things that we needed to remember from the past to kind of weave it together. It's also a really good example of you can't memorize like proofs. You have to know them. You have to know what's going on and how they weave. Now, why do we do things like this? Applications. Say I have these points, 1, 2, 3, 4, 5, 6. So I have my point 1 to point 6. And say point 1 is 1, 1, and point 2 is equal to 2, 2, and then point 3 is 3, 1, and then point 4 is 4, 3, and point 5 is 2, 2 again, and then point 6 is, say, whoops, not 2, 5, 2. And point 6 is, say, 6, 3. One of the things that you do when you collect data like this, if this is data collection, one of the things that we would take on a problem like this is we would like to fit it with particular polynomials. I'd like to have a polynomial. Now, if you have 6 points, you could perfectly fit this to a polynomial, say p of x equaling a plus bx plus cx squared plus dx cubed plus 4. ex to the 4th plus fx to the 5th, right? How many unknowns do I see? There's 6. That means that if I plug in 1 for the x's, it should equal 1. That's a single equation. If I plug in 2 for the x's, it needs to be equal to 2. That's my second equation. If I plug in 3 in for x's, it should be equal to 1. That's my third equation. If I plug all of these into it, I will get a 6 equation, 6 unknown problem. And what I will do is I will get a polynomial of degree 5 that goes perfectly through those points. But what you'll notice is it starts to get really wiggly. And you sit there and say, if this is a collection of data, do you really believe that if you had this point and this point, that if you would have collected the data points, it would bend down like that much. And like the more data points you'll get things like this thing goes all the way up to nearly infinity and then comes back down rather quickly. If you go through if you have 6 points and you fit it with a 6-term polynomial, that's called the interpolating polynomial. They tend to be bad because they have this really crack the whip effect. Normally you would look at this and say, in real world applications, this most likely is not this polynomial. It's most likely, say, a polynomial that might do something like that, which is a lower degree polynomial. So if I use 6 terms, it's called an interpolating polynomial. But on the other hand, if I would rather use, say, q of x equaling a plus bx plus cx squared, then my problem has how many unknowns? 3. But when I plug in all my 6 points, I'm going to have how many equations? 6. So now I have an overdetermined problem. So when I put this thing in, if I would take these particular points and plug it in for that, then this would rather become, for these q's, it would look like this. It would have the constants, which would be 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, and then my x's, which would be 1, 2, 3, 4, 5, 6, and then I would square it, 1, 4, 9, 16, 25, 36, all times A, B, C should spit out 1, 2, 1, 3, 2, 3. So that, finding A, B, and C is solving this system. Well, this is an overdetermined system. And if you'd calculate the rank of this, the rank better be 3, and I'm making a reasonable guess. I just threw it in there. I'm going to assume that the rank is 3, right? And so it is. And so the rank of this particular thing here, this particular one, notice how it goes constants x, x squared. If I would do an x cubed, I would have the cubes and the fourths. That's this particular matrix here, which is the matrix of the powers of x's. It's called the Vandermonde. Since you're doing data fitting all the time, it gets its own name. So it's like Vandermonde. So how do I solve this? Well, I would call him A, I would call him C, I would call him Y. And it's like, well, how would I solve it? Well, it has no solution. There is no parabola that goes through these 6 points. So since it has no solution, we could stop and say it's inconsistent. No parabola goes through this. Or we reinterpret the problem and say, let's find the least squares data solution. And so this has no solution. We have no parabola through those 6 points. And so rather what we do is the least squares problem, which is to rather solve A transpose A C is equal to A transpose Y. And the solution is, what are the coefficients? It is A transpose A inverse times A transpose Y. And we could obviously do that by hand. This is where, like on a problem like this, just doing by hand, this is where you use things like normally computational tools, like Octave, MATLAB, Sage Math, things of that nature to actually do it. But obviously, if you want, you could take that matrix and this vector, take the transpose of this matrix. What's the size of this? 6 by 3. If I transpose it, it is 3 by 6. So a 3 by 6 times a 6 by 3 is a 3 by 3. And so this problem would become a 3 by 3 times ABC 3 by 1. And then you solve it, and you'll find the coefficients of the parabola that is as close as possible, and it wouldn't have this downward curve like that, obviously. I should have gone to one extra term if I wanted to have 2 bends in it. But it'd be the parabola that's as close as possible with the least amount of square error. And tons and tons and tons of math problems are for systems like this. Actually, give that a shot. Finish that on home just for fun. Everybody knows how to do it. You want to multiply big things. All right, that's it.
Can you sort of